Welcome students, welcome back to chemical technology. In last modules we have discussed about the sulfur and sulfuric acid industry. So in these coming modules we will try to discuss about the nitrogen industry. It's a major industry in the Indian scenario because Indian economy is based on agriculture and agriculture is based on food production, and the food crop production is based upon the nitrogen content in the soil, and that nitrogen content in the soil we are providing by means of fertilizers. The fertilizers, it is a product of the nitrogen industry. So hence the learning of nitrogen industry is essential as far as the Indian scenario is considered. So in today's module we will try to discuss about the nitrogen industry, then the various methods and the various chemicals which is a product of nitrogen industry, that are ammonia, the nitric acid, the urea, ammonium nitrate, and we will discuss other chemicals also. They are ammonium sulfate, ammonium phosphate, sodium nitrate, potassium nitrate, cyanamide, ammonium chloride. So you know the N2, the nitrogen is present and abundant in air and can be fixed to ammonia by reacting with the hydrogen. So nitrogen, which is a part of the air, and we know it's in high percentage than any other gas, so that we can directly react with the hydrogen, and we can have the ammonia, and ammonia we can process further to get the other chemicals. So this is used for low cost chemical supply and mainly in the fertilizer industry. So the mostly of them we use as the nitrogen fertilizers to give the nitrogen to plants. The nitric acid we can use for the fertilizers, or we can use to produce the other chemicals. Then as far as the Indian economy is based on agriculture and agriculture based on fertilizers, nitrogen industry plays important role in it. So the Indian economy, which based on the agricultural and in turn which based on the fertilizers, so nitrogen indirectly plays an important role in the Indian economy. Then while studying the nitrogen industry, we will give the major priority and emphasis on the fertilizers which are produced in the nitrogen industry. Starting with the ammonia, so it is given by NH3, and we know it's a tetrahedral geometry having the angle 107. So it's a distorted angle because of the lone pair present on the nitrogen. So while discussing about the properties, the molecular weight, it has 17.03, the melting point minus 77.7 degrees Celsius, then boiling point is minus 33.4 degrees Celsius. So ammonia mainly present in the gaseous form, and it is very soluble in the water. So the water and ammonia, they form the NH4OH, that is liquor ammonia. So mainly it is transported while soluble in the water form, and we have seen in the laboratory it is mixed with the water to form the liquor ammonia. And when we expose to the heat, the ammonia slowly evolves from the liquor ammonia. Then the grades we have the anhydrous, means without water, or the liquefied the ammonia stored at 80 degree Fahrenheit with pressure of 175 psig. Also we can have the aqueous grade of the ammonia, which contains 28% of the ammonia. Then if you see the consumption pattern of the ammonia worldwide, so mainly it is used directly as a fertilizer up to 25%. Then in urea, which is used for fertilizer and plastic industry, it is 21%. Then the phosphates 16%. And production of nitric acid 12% is utilized. Then others is 12%. The ammonium nitrate and sulfate, they will represent 8% and 3% respectively. And the acrylonitrile again is 3%. So you can see ammonia used for the various kind of the production of the chemicals. So mainly it is used in the production of the fertilizer. So this is fertilizer, here is the fertilizer, and here if you see the figure, the more than 50% goes in the fertilizer directly. So we will discuss the fertilizer pattern of the nitrogen. So it is used to produce the mixed fertilizers, and principal elements are the nitrogen, potassium, and the phosphorus. So this is denoted as NPK. So if you have seen the fertilizer bag, you have notice they have written NPK with some numbers over it. So the composition is expressed as weight percentage of total nitrogen and available the phosphorus pentoxide and soluble potassium oxide. Example, suppose a bag written over here 5, 10, 5. So that will denote 5% of nitrogen, then 10% of the phosphorus in the form of phosphorus pentoxide, and the 5% of K2O. So in fertilizer bag, if we have seen this kind of number, then you can relate as this one. What is the nitrogen content, what is the phosphorus content, and what is the potassium content. And it is generally in the granular solids. So why? Because the granular solids, they are easy to transport or they are easily soluble also. If you have in a powder form, it may be carried away by the wind. So it's better to have in the granular forms. So generally, all the fertilizers we can make in the granular solids form. So the manufacturing of the ammonia, so the all processes are based on the pressure catalytic reaction of nitrogen and hydrogen. So basic materials are the nitrogen and hydrogen that we are reacting to get the ammonia. The principal variation is in the operating pressure. So the N2NH2 operating pressure, that will decide the process. So the reaction is follows: the nitrogen and hydrogen, which is reversible reaction, in presence of the ion catalyst we can have the ammonia, and it is a exothermic reaction and involves the heat. So K equilibrium we can have like this one: the pressure of the ammonia and the pressure of the nitrogen and hydrogen. So we can shift these to get ammonia by suitable modification of the conditions. So we will discuss in the thermodynamics. So the raw materials are here: the hydrogen from the synthesis gas and the nitrogen from air addition in synthesis gas process or from air liquefaction process. So H2, which is majorly come from the synthesis gas or maybe the byproduct of the refineries, and then N2, which is from air, which can be separated from other gases, and we can use to carry out the reaction of the N2NH2 to get the ammonia. So if we see the reaction constant over or equilibrium constant over here, so it is a function of the temperature. So how it varies? So temperature increases, then we can see the K equilibrium is decreases. So you have to maintain the temperature in such a way that it gives the maximum rate. So here what happens, as being the exothermic reaction, so already we discussed in the sulfur and sulfuric acid industry, so the high temperature will reduce the rate of reaction or will reduce the K equilibrium. So this is given by the NH3 in the denominator. So here what happens, when NH3 we have to increase, then we have to decrease the temperature. But low temperature will again reduce the NH3 formation. So NH3 is in numerator and the reactants are in the denominator. So here the K equilibrium will be high when NH3 is high. Then NH3 is high when the reaction rate is forward one or reaction is going in forward direction. So that we have to keep in mind. So here the temperature, it should not be very low or should not be very high. We should have the optimum temperature. And also pressure of N2NH2 should be very high so that the effective conversion is very high to get the ammonia. So here ammonia synthesis gas. So 3 mole pure of H2 is to 1 mole of pure N2. So as the stoichiometry suggests, we have to get the 3 mole of H2 and 1 mole of nitrogen, which is compressed at very high pressure, that is around 100 to 1000 atmospheres, and it may be vary depend upon the conversion. Then it is passed through a filter to remove any impurities present over it, then passed over a porous ion catalyst at around 500 to 550 degrees Celsius, then 8 to 30% conversion achieved, which is removed by condensation, and then unconverted mixture again recycled to achieve 85 to 90% of the conversion. So H2 to N2 in 3:1 ratio we have taken, then we are filtering, then passing over a catalyst at a temperature, then we get some conversion, and to have achieve high conversion we are recycling back. So this is the process flow diagram for the NH3 production. So here the purified NH3 gas, purified NH3. So here what we have the 1 mole of N2 and 3 mole of H2. Then we are compressing it, and then oil filter to remove any compression oil over here. Then feed guard converter, which is optional one, to remove any impurities which may attack the catalyst. So this may be the optional. Then we are feeding to the reactor. So cold gas comes over here, and then temperature it will rise from 500 to 600, which is the reaction temperature, and it may have the pressure of 100 to 1000 atmosphere. So you see over here, the cold gas is passed, and here temperature, the pressure is very high. So we have to use the vessel or reactor which can sustain this high pressure. So in order to have the high pressure sustainability, we should have the cold reactor. Means we have to cool the reactor by means of the coolant. Then reaction will take place around 500 to 600 degrees Celsius, and then the converted ammonia we are cooling in two stages, one by the simple water or the cooling water, and then we can separate the unreacted gases and we have the ammonia, or we can send to the NH3 refrigerant which is at minus 15 degrees Celsius and we get the ammonia. So this is cooling by water and cooling by the NH3 refrigerant, and we get the ammonia and we can have them in a spherical tank storage. Whereas the unreacted gases, they are sent to the recycle. So centrifugal recirculator will recirculate the unreacted gases. So they are either sent to the reactor again, or they may be the small purge stream to prevent accumulation of diluents such as argon. So here if suppose argon is in high concentration, then we can simply purge it, or if N2 and H2 they are in the quantity, then we can pass to the reactor. So the conversion here in first pass is 8 to 30%, then we are again recycling it back to get an higher and higher conversion. And then NH3 we can store in the spherical tank. So the N2 and H2 compress, that filter, oil filter to remove oil, then impurities removed, fed to the reactor which is operating at a very high pressure. Ammonia which we get, we are cooling with cooling water or NH3 refrigerant, and we are sending to spherical tank, whereas the unconverted we are feeding to the recycle or we are simply purging out. So what we have the major engineering problem in this process. So if we see the thermodynamic and kinetic consideration, the highest equilibrium yield can be achieved by high pressure and low temperature. So this is given by this equation. So yield of ammonia, so here we can see it is a function of high pressure and the temperature. So the yield of ammonia we get when we have the high pressure and the low temperature. So this is being exothermic reaction, low temperature will favor the forward rate of reaction, and whereas the high pressure, that will the reactant side is high, then it can push the rate to in forward direction. So here the equilibrium constant is an inverse function of the absolute temperature. So the low temperature will favor the reaction more. And here if we see this equation which gives this phenomena, so here we can see the Kp is a function of inverse of the temperature. So to deal with this problem, we have multi-stage operation like SO2 to convert SO3 conversion, but it's not economical in H3 as high pressure vessels used as a reactor. So what happened in order to achieve the high pressure and low temperature? So we have seen the sulfur trioxide conversion from SO2. So there we have the multi-stage heat absorbers or heat exchangers which were cooling the gases and again feeding to the reaction. So what was happening over there? Due to the low temperature, the unreacted SO2 they are converted into SO3. Because high temperature, the conversion will be reduced. Same thing we can do in case of the NH3, but the problem is it's not economical because we are using the high pressure vessels. So if you have the multi-stage operation, then you have to use the high pressure vessels. So the process overall becomes the non-economical in this case. So we have to rely on the high pressure, and we have to see which condition we can maintain so that the reactor will achieve the low temperature and the high conversion. So thus design problem thus reduces to an optimization of the space velocity based on the fraction of ammonia at exit decreases as the flow rate increases in inlet. So here one thing we can do, the space velocity means the flow at which the reactants are fed to the reactor. So more is the space velocity, more is the conversion. But here what is the problem, that the space velocity is very high or the flow rate is very high, then the fraction of NH3 at the exit decreases. So more the space velocity, then it will decrease. So again it's the problem. Then in addition to high space velocity, to cool bed which is at high temperature, so in order to achieve the low temperature of the bed, what we can do, we can pass the more airflow to cool the bed. But here increases costs of ammonia recovery as fraction is lower. So more is the gas, it will be cooled, but when it's cooled, the ammonia also getting diluted with the air in the reactant. So we have to expense for that one. Then as we are pumping more gases, the pumping cost is also high. So we want low temperature so that we are passing more air, but that is giving the cost of ammonia recovery and the pumping cost also. So we have to find the optimization of this reaction. So in curve we can see the space velocity and the cost in rupees per kg produced. So if we see the cost increases, so for NH3 recovery, as the space velocity increases, the cost of recovery also increases. Then reactor cost. So you can see the space velocity increases, then reactor cost will slowly decrease as we gauge the more conversion over here. Then pumping cost, we know more airflow, so more pumping, so pumping cost is directly proportional to this one. So linear graph we can see space velocity increases, the cost also increases. Then X, which is the fraction, so airflow more, the fraction will be low. But if we see the total cost of this one, so it has achieving minimum at this point. So at this point, we have to consider the space velocity. So this much space velocity if we keep, then the reactor cost will be this one, then NH3 recovery cost will be this much, then the fraction of NH3, the pumping cost, and the yield. So we have to go for the optimization. So this kind of curves we already discussed in the managerial economics. So we can refer. So these are the optimum condition of the NH3 production. Then the next step is catalyst development. So catalyst is very essential to get the conversion. So it should give the more yield at a lower temperature and pressure, thus lowering the cost. So you have to choose such a catalyst which can give the reaction at a low temperature and also at a low pressure. So that will reduce the cost tremendously. Nowadays the catalysts we are using, they are based on iron oxide with alkali promoters as the K2O 1 to 2% or Al2O3 2 to 5%. The iron oxide is fused and promoters are added and then grounded to desired sides. Then what we are doing, the iron oxide we are fusing, then we are adding these promoters and then cooled down and then grounded to desired size. A promoter catalyst is developed in Europe, works at a lower temperature and pressure condition. So the new catalyst development is taking place which can work at low temperature and pressure. So Europe has already taken lead in this catalyst development. If we see the worldwide production of the ammonia, we can see India, which is based on the agricultural, they have the higher production of the ammonia. Also in China we can see the higher production of the ammonia. So after ammonia, the major chemical of the nitrogen industry is the nitric acid, that is HNO3. So we can see, so transition is taking place, so between the two O atoms, so the HNO3. So molecular weight 63.03, then melting point is minus 42 degrees Celsius, boiling point is 86 degrees Celsius with decomposition. It is completely miscible with water and forms a constant boiling mixture at 110 degrees Celsius and 760 mm of Hg, which contain 68% of HNO3. then grades, we have the concentrated, which is more than 95%, then fuming, it is more than 86%, then red fuming more than 95% with 10 to 15% excess oxides of nitrogen. Then nitrating, it's a 50 to 80% HNO3 with 15 to 48% of the H2SO4. So these are the physical properties of nitric acid solution at 20 degrees Celsius. So you can see the HNO3 weight percent and the corresponding the boiling point at 101 kilopascal. So we can see for 20% it is 104.4, and the partial pressure of the water is 1.61, density is 1.18, and whereas the specific heat is 3.18. So you can see the variation in the specific heat as the variation in the percentage HNO3. Then the nitric acid is mainly used to form the adipic acid, which is 9%, then dinitrotoluene 3.5%, nitrobenzene, which is used for the aniline production, which is 3.5%, then the sodium, the potassium, calcium nitrates 2%, the nitro compounds for explosives 1%, and the other is 5%. So the rest 76% of the ammonium nitrate, of which, so out of 76%, 80% for fertilizers and 19% for the explosive and 1% for the N2O. So you can see the ammonium nitrate production. So HNO3 is a major part of the ammonium nitrate, and which is again is the major part of the fertilizer and explosives. So we have the various methods of the production of the nitric acid. The first one being the ammonia oxidation process, and this accounts for 90% of the production and divided into the four fundamental steps. That is, first one is oxidation of ammonia to NO, then oxidation of NO to NO2. So this takes place in a separate reactor. This takes in a separate reactor at different temperatures. Then absorption of NO2 in water and the concentration of HNO3. Then that NO2 is added to water to get the nitric acid, and the concentration of nitric acid we can done by use of the other chemicals such as sulfuric acid and magnesium nitrate. The next process is the NaNO3 plus H2SO4 process. The next one is N2 fixation from air, that is Wisconsin process, and the nitrogen fixation by nuclear fission fragments. So we will mainly discuss about the ammonium oxidation process. So in ammonia oxidation process, we have the ammonia oxidation, that is major reaction. So ammonia is oxidized to form the NO. Then the side reaction may take place producing the nitrogen, then N2O. And then we have the nitro oxide oxidation and absorption to form the NO2, and then NO2 with reaction with the water we can have the nitric acid. So you can see all the reactions are exothermic, so tremendous amount of energy is released in the reactions. So the raw materials for this one is NH3 from the synthetic ammonia process that we have seen earlier. The nitrogen and hydrogen combine and getting the NH3. Then we should have the filtered air. Then platinum rhodium makeup catalyst. The plant capacity was is 50 to 250 tons per day per unit, and a plant may have the 3 to 5 units. Then suppose if we are producing 1 ton of HNO3, which is 100%, then we require anhydrous NH3 0.287 to 0.290 ton. The air we require is 3000 Newton meter cube. The platinum 2 to 10% rhodium promoted platinum rhodium makeup catalyst is around 0.1 gram. Then the process water we require 120 tons. The steam credit is 1 ton at 200 psig, and the power required is 10.3 kilowatt per hour. So we have to discuss about the Montecatini intermediate pressure process, and there are various processes, but main thing is they are oxidizing the NH3 to NO, then NO to NO2, and then to the nitric acid. So what we have? We have the compressed air and anhydrous ammonia is fed to a shell and tube converted and then passes over a catalyst, that is platinum rhodium, in the form of 60 to 80 mesh wire gauge. So here we can see the catalyst in many plates. So these are mounted on the 60-80 mesh wire gauge, and many plates we can see in the reactor. So generally it takes the compressed air and the anhydrous ammonia. So the oxidation of this, it takes place over the platinum rhodium catalyst. Then contact time we are keeping around 250 microseconds and temperature around 800 degrees Celsius to get the NO. Then the 10 to 12% NO so form, and heat is recovered and sent to the oxidizer absorber where air is added to convert into NO2. Then that NO2 we can convert into nitric acid by use of the water. So the 57 to 60 degree HNO3 solution sold as it is or concentrated. Then the concentration, if you want more concentration than this, then we can concentrate by 95% or 66 degree above H2SO4 or with the help of 70 to 75 magnesium nitrate solution. Later is advantageous in terms of the cost, capital and quality yield. So mainly this is used as a concentration. So this is used to convert NO. This is the contact time and the temperature. Then NO to NO2, this will happen, and then NO2 to nitric acid.